honor to chair this session. And today we will have two great speakers. The first one is Song Peng from Singapore University of Technology and Design. The second speaker is Haisen Zhao from Shandong University. And each speaker will have 45 minutes, including discussions. And to our audience, please do not hesitate to post your questions in the chat box, no matter what channels you are watching this live channel. So firstly, I will introduce the first speaker, Song Peng or Peng Song. He will talk on computational design of geometric puzzles. And Professor Peng Song is an assistant professor of computer science at Singapore University of Technology and Design. Prior to joining SUTD in 2019, he was a research scientist at EPFL, Switzerland, and an associate researcher at University of Science and Technology of China. He received his PhD from Nanyang Technological University, Singapore in 2013, and his research interests lie in computer graphics with a particular focus on geometry modeling and computational design. He received SIGGRAPH Technical Papers Award Honorable Mention in 2022, co-organized a virtual seminar series on computational fabrication in 2021 and 2022, and has served as the program committee on many international conferences, including SIGGRAPH Asia, Pacific Graphics, and Symposium on Solid and Physical Modeling, or SPM. So welcome, Professor Peng Song, and now the channel is yours.
Okay, thank you, Professor Nuni, for the kind of introduction. So let me share my screen.
Yeah, it's great.
Okay, so you can see my screen, right?
Yeah.
Okay, thank you for the introduction. So it's my great pleasure to give this talk at the AsiaGraphics webinar. In this talk, I will first give an overview of research in computational design of geometric puzzles, and then I will introduce my recent research works in this topic. So first, what is a geometric puzzle? A geometric puzzle is an arrangement of a set of puzzle pieces to form a meaningful 2D or 3D shape. The most well-known geometric puzzle is jigsaw puzzle. The task of playing jigsaw puzzle is to assemble the puzzle pieces into a tagged shape, usually a 2D rectangle. There are various kinds of geometric puzzles, including jigsaw puzzles, polynomial puzzle, where the task is to assemble a set of pieces that are composed of equal squares. Disentanglement puzzle, where the task is to disentangle one piece from the other piece. Kioski puzzle, a sliding block puzzle, where the aim is to move a specific block to some predefined location. And balance puzzle, where the puzzle should stand in balance by itself when all the puzzle pieces are put together. Interlocking puzzle, where all the puzzle pieces interlock with one another, forming a steady puzzle structure. Dissection puzzle, where a set of puzzle pieces can be assembled in different ways to produce two or more distinct geometric shapes. And sequential movement puzzle, such as the famous Rubik's Cube, where the puzzle can be solved by progressing from some initial state to some goal state using sequence of moves. Among all these geometric puzzles, the task of jigsaw puzzle and polynomial puzzles is to assemble the puzzle pieces to form a 2D shape. People usually playing these puzzles on a planar surface, such as a table or ground, such that all the puzzle pieces can be supported by the planar surface. Similarly, balance and interlocking puzzles also focus on the assembly process. The difference is that the puzzle pieces supported by one another to form a steady 3D puzzle structure. Disentanglement and Kioski puzzles focus on disassembly, aiming to take out one or more puzzle pieces. while dissection and sequential movement puzzles focus on reconfiguration, meaning that once you disassemble the puzzle pieces in one state, transform them and reassemble the puzzle pieces to form another state. From this explanation, we can see that puzzle solving can be formulated as an assembly planning problem when we put a set of puzzle pieces together to form a meaningful shape. It can also be formulated as a disassembly planning problem, where we move a set of puzzle pieces to reach a configuration where a targeted puzzle piece can be taken out, such as the green piece shown in this example. Assembly planning is a very fundamental problem that is important not only in puzzles, but also in many other disciplines, such as architecture, engineering, and robotics. Assembly planning is the process of creating detailed instructions to combine separate parts into the final structure. Assembly planning will output three kinds of information for the assembly process. First, an order to assemble the parts, or called assembly sequence. In this example, we first assemble the orange part, followed by the blue, yellow, cyan, and green parts. Second, motion to bring each part to its target pose, called disassembly path planning. In this example, for the blue, yellow, and cyan parts, we translate each of them from left to right. And for the green parts, we translate it downward for the assembly process. Third, utilization of additional resources for the assembly process, such as supports and tools. Look at this intermediate assembly. The blue part is held by using a support in order to assemble the yellow part. Similarly, we add a support to hold the yellow part in this intermediate assembly in order to assemble the cyan part. This assembly planning is a reverse process of assembly planning. A bijection exists between assembly and disassembly sequences and passes if we consider only geometric constraints. And this enables an important strategy for assembly planning called assembly by disassembly. In this strategy, we first compute a disassembly plane for a given assembly, and then we obtain the assembly plane by reversing the disassembly plane. The advantage of this strategy is to dramatically reduce the size of the solution space for searching the valid assembly planes. This is because parts in an assembled state have far more precedence and motion constraints than in the disassembled state. Classification of disassembly planes. Disassembly planes can be classified as a sequential and non-sequential. A sequential plane is also called two-handed plane, meaning that you can always use two hands to disassemble the parts. See the top example. The bottom example shows a non-sequential plane or a three-handed plane. We need three hands to disassemble it. One hand fixes the orange part, one hand moves the green one, and one hand moves the cyan one at the same time. An assembly is monotone if no intermediate placement operations are needed for the assembly. See the top example. The bottom example shows a non-monotone plane. This is because at the first step, we need to move the green part to the right in order to take out the cyan part. An assembly plane is linear if all assembly operations involve moving a single part with respect to the rest of the assembly. See the top example. The bottom example shows a non-linear plane. This is because in the first disassembly operation, we need to move two parts together in order to disassemble them. A coherent plane means that each part that is moved will touch the rest of the assembly. See the top example. The bottom example shows a non-coherent plane. This is because when we move the orange part, it does not touch any part in the rest of the assembly. To avoid making puzzle too complicated to be solved, most geometry puzzles assume sequential, monotone, linear, and coherent assembly plans. That means to solve a puzzle, we should assemble the puzzle pieces one by one, following an order. When inserting a puzzle piece, it should touch the assembled puzzle pieces and directly reach its final destination in the puzzle. However, some geometry puzzles assume more complex plans. For example, coordinated motion puzzles requires a non-sequential plan to assemble or disassemble the puzzle. That means we cannot solve these puzzles by assembling the puzzle pieces following an order. Rather, all the puzzle pieces move simultaneously along different directions when we assemble them. Curiosity puzzle assumes a non-monotone, linear or nonlinear disassembly plan. That means we need many intermediate placements of the puzzle pieces in order to take out the green piece. When moving the puzzle pieces, we can either move a single puzzle piece or a subset of puzzle pieces along the same direction. This tanglement puzzle assumes non-coherent disassembly plane. That means when we solve these puzzles, the puzzle pieces may not contact one another, making it difficult to find a correct solution to disassemble the puzzle piece. So now we know that solving geometry puzzles requires finding different kinds of disassembly planes. But how can we find a feasible disassembly plane by using computers? We take this 2D puzzle as an example to illustrate how to find a sequential, monotone, linear, and coherent disassembly plane. Since the disassembly plane is linear, it means that we are allowed to move a single puzzle piece at a time. The approach is to identify a movable puzzle piece in the puzzle, such as the green piece. And then we remove the movable piece from the assembly. And next, we identify the cyan piece as the movable one and remove it from the assembly. We iterate this process until there is only one puzzle piece remained in the assembly. So the complexity of identifying a movable puzzle piece is bigger O n, where n is the number of puzzle pieces. For some puzzles, there may not exist a linear plane to disassemble it. Look at this example. There is no individual piece that is movable. If we only allow linear disassembly plane, then this puzzle is not solvable. However, this puzzle can be solved by using a non-linear disassembly plane, since there exist two sub-assemblies that are movable. The sub-assembly with green and cyan pieces can move to the right, and the sub-assembly with blue and yellow pieces can move to the left. Hence, we can identify a movable sub-assembly in the puzzle, and then remove the sub-assembly from the puzzle and disassemble it. We iterate this process until there is only one piece remained in the puzzle. The complexity of identifying a movable sub-assembly in the puzzle is big O 2 to the power n, since there are 2 to the power n combinations of the puzzle pieces. To speed up the approach, we can build directional blocking graphs for the puzzle. Then we can identify a movable sub-assembly as a strongly connected components in the graphs. And next, we can remove the sub-assembly and disassemble it. This approach is much faster than the first one, since there exists algorithms with big O n to the power 2 complexity to identify strongly connected components in directed graph, which are the sub-assemblies that are movable. Non-sequential and coherent planes. Look at this example. There does not exist a sequential plane to disassemble the puzzle, since there is no individual piece that is movable and no subassembly that is movable. However, there indeed exists a non-sequential plane to disassemble the puzzle pieces, where the green piece and the blue piece move along different directions simultaneously. To identify a non-sequential disassembly plane, we can model the puzzle assembly as a rigid body system. In this rigid body system, we allow each puzzle piece to move freely in 2D or 3D space, except fixing one puzzle piece as a reference. The constraint is to avoid collision between the puzzle pieces at each contact during their infinitesimal moment. By stacking all the non-collision constraints for every planar contact between the parts, we obtain a system of linear inequalities By are larger than or equal to 0, where y is the generalized velocity of the rigid body system. B is the matrix of coefficients for collision-free constraints. By using this method, we can find this collision-free motion to take out the green and cyan parts. See the green and blue errors. Non-monotone and coherent planes. To identify a non-monotone disassembly plane for this Kielowski puzzle, we can build a puzzle configuration graph where each node is a puzzle configuration and each edge is a disassembly operation. A disassembly plane is a path from the start node to the target node in the graph. We will introduce more about this data structure later. Finding a non-coherent plane is a challenging task, since each puzzle piece can move without contacting each other. Each puzzle piece has a large motion space, usually 6 degrees of freedom motion in 3D. And our disassembly planner needs to ensure that there is no collision among the puzzle pieces during their movement. A recent work by Zhang et al. Has addressed this problem for solving a 2-piece disentanglement puzzle. And the idea is to match geometric features of pieces to discover collision-free puzzle states, and to find a disassembly path to connect start and goal states in the puzzle configuration space. So now we know that the puzzle solving can be formulated as an assembly planning problem, where the goal is to assemble a set of puzzle pieces to find a meaningful shape. In contrast, puzzle design can be formulated as a geometry modeling problem. The goal of puzzle design is to model geometry of puzzle pieces while satisfying various design requirements in fabrication, assembly, appearance, reliability, and so on. Obviously, puzzle design is a more challenging task than puzzle solving. This is because when we design a puzzle, we have to ensure that the puzzle can be solved. That means once a puzzle is designed, its solution should be already known. Puzzle design is a challenging geometry modeling problem since there are many requirements that have to be satisfied. There are 4 basic design requirements for all kinds of geometric puzzles. First, the design puzzles have to be solvable, meaning that there exists collision-free motion to assemble the puzzle pieces. Second, the design puzzle should have a meaningful 2D or 3D shape in order to make the puzzle attractive. Third, designers should be able to specify the number of puzzle pieces. And each design puzzle piece should be fabricable. For example, each puzzle piece should not have a disconnected geometry. Besides the basic design requirements, some puzzles have some advanced design requirements, including similar puzzle piece, reconfigurable puzzle, and structurally stable puzzle. Traditionally, design of geometric puzzles is limited to skillful craftsmen with great effort. They make hours or even days of mental work to design a single puzzle. The other approach is to use computers to exhaustively search all possible configurations in the design space. And a more widely used design approach is to use computers to assist the design process. For example, check whether a design puzzle is solvable. This traditional design approach have two limitations. First, they can only explore a small design space. And second, they require many design and prototyping iterations to find a good puzzle design. Recent advances in digital fabrication enables general users to make puzzles easily and inexpensively. These digital fabrication techniques take the geometric model of a puzzle as an input and output a physical copy of the puzzle. However, designing a personalized puzzle remains a challenging task. To address this challenge, in recent years, many computational approaches have been developed by the graphics community for designing personalized puzzles. These computational tools take a user's high-level specifications on the puzzle as input and directly output puzzle designs that are ready for fabrication. These computational approaches have several advantages over the traditional ones. First, they enable general users to design personalized puzzles. Second, these computational approaches can explore a large design space of puzzles. And third, they enable an efficient design process by reducing the number of design and prototyping iterations. Here, I will give an overview of recent research works on computational design of geometric puzzles. These two research works have been done for designing 2D and 3D jigsaw puzzles, respectively. Since puzzle pieces in jigsaw puzzles have similar shape, the puzzle design problem is typically formulated as a 2D or 3D tiling problem, where each tile is a piece shape. There are also two research works on computational design of 2D and 3D polynomial puzzles. Since the puzzle pieces in polynomial puzzles have a few classes of shapes, the puzzle design problem is also formulated as a 2D or 3D tiling problem. Dissection puzzles have multiple distinct shapes and can be reconfigured among these shapes. To design these puzzles, multiple shapes, usually two shapes, are taken as input, and the puzzle pieces can be generated by code decomposition. Interlocking puzzles are structurally stable when all the puzzle pieces are put together. Starting from the pioneer work by Xin et al., we have developed several computational approaches for designing interlocking puzzles. Design of interlocking puzzles is typically formulated as a shape decomposition problem. In this talk, I will introduce two pieces of recent research work in this topic. A puzzle with rigid parts is structurally stable if it can preserve its form under external forces without collapse. Structure stable is a necessary condition for playing 3D puzzles. Computational methods can be developed to analyze whether a given puzzle is structurally stable or not. One typical method is static analysis. It can tell us if a given puzzle is in equilibrium under a certain external force. However, a lateral force, such as those from an accidental touch, can easily make the collapse. In practice, a puzzle should be in equilibrium not only under gravity, but also under lateral forces. So tilt analysis is a process to quantify this lateral stability. In an extreme case, a puzzle can be in equilibrium under arbitrary external forces, and we call this structural stability state interlocking. Comparing these three states, we can see that the puzzle becomes more and more structurally stable, and the cost is that the geometry of the puzzle pieces become more and more complex, since more restrictive joints are needed to connect the pieces. We know that a puzzle is interlocking if it is in equilibrium under arbitrary external forces. Here we define interlocking based on the statics. However, trying all possible external forces is infeasible in practice. Thanks to the static kinematic duality, we can define interlocking based on kinematics. A puzzle is interlocking if there is no movable part or subassembly except the key. More precisely, an assembly of puzzle pieces is said to be interlocking if there exists only one movable piece, while all other pieces, as well as any subset of the pieces, are immobilized. Okay, this example, the puzzle piece can assemble following a certain order. And once assembled, there is only one movable piece called the key, which is the green one shown here. If we hold the key, no puzzle piece can escape from the assembly. In case that the puzzle pieces are not properly designed, the assembly could be non-interlocking, in which multiple puzzle pieces and sub-assemblies are movable. The puzzles are also possible to be deadlocking, meaning that the puzzle cannot be physically assembled. From this definition, we can see that the complexity to test mobility of all sub-assemblies has an exponential complexity with the number of puzzle pieces. Given two puzzles with the same overall shape and the same number of puzzle pieces, they may have different levels of difficulty in terms of disassembly. Look at these two examples. The left puzzle requires a single move to take out the green piece, while the right puzzle requires 5 moves to take out the first piece in green color. Level of difficulty of an interlocking puzzle is assessed by the minimum number of moves required to remove the first sub-assembly from the puzzle. Here we need to define move of a puzzle piece or sub-assembly more precisely. A move is counted as one irregardless of how far a piece is moved in one direction. Look at the pink piece, it moves downward for 2 pixels distance, and this operation is counted as one move. The move to remove a piece or sub-assembly is counted for one move, such as taking out the green piece on the right. Moving 2 or more pieces in the same direction simultaneously is one move, such as move the yellow and blue piece to the left at the same time. The level of difficulty of this interlocking puzzle is 5, since it requires 5 moves to take out the green piece, and its disassembly plane is non-monotone, linear, or nonlinear. Based on the level of difficulty, we can classify interlocking puzzles into 2 classes. Conventional interlocking puzzles, which require a single move to take out the key piece. In other words, the level of difficulty is always 1. The second class is high-level interlocking puzzles, which requires multiple moves to take out the first sub-assembly. Here is a comparison between these 2 classes of interlocking puzzles. Conventional interlocking puzzles has a level of difficulty equal to 1, while high-level interlocking puzzles has a larger level of difficulty. For conventional interlocking puzzles, the number of puzzle pieces can be as large as possible, since the assembly plane is relatively easy. However, for high-level interlocking puzzles, we assume a small number of puzzle pieces to ensure pliability of the puzzle. For conventional interlocking puzzles, we assume a sequential, monotone, and linear disassembly plane. While for high-level interlocking puzzles, we need to use a sequential, non-monotone, linear, or nonlinear plane to disassemble the puzzle. Due to the above different characteristics, the challenge to design conventional interlocking puzzles is to ensure interlocking for a puzzle with a large number of puzzle pieces, while the challenge to design high-level interlocking puzzles is to ensure that the plane to disassemble the puzzle should be as complex as possible. We have developed a computational approach to design the 2 classes of interlocking puzzles respectively. The research work about designing conventional interlocking puzzles has been published in Seoul of Asia 2018, while the research work about designing high-level interlocking puzzles has been published in Seoul last year. Okay, so let's talk about the first research work. To design a conventional interlocking puzzle, our input is a Volkswagen shape as the number of puzzle pieces n. Our output is the geometry of the n-piece interlocking puzzle with a given shape. This puzzle design problem can be formulated as a shape decomposition problem. And the shape decomposition should satisfy the 4 basic design requirements: assemblable, meaningful shape, number of puzzle pieces, fabricable puzzle pieces. Note that we assume sequential, monotone, and linear disassembly planes. To satisfy the basic design requirements, we propose a design framework based on iterative shape decomposition. Starting from the input shape, we decompose it to extract the first puzzle piece P1, and the remaining puzzle is called P1. Next, we decompose R1 to extract the second piece, and we iterate this process until it generates n puzzle pieces. We can ensure that the resulting puzzle is assemblable by requiring that the PI can be taken out from P1 R1. And the factorable of puzzle pieces requirement is satisfied by ensuring that each extracted puzzle piece has connected geometry. Okay. Now the problem is how to ensure interlocking for the puzzle results from the shape decomposition. The challenge is that naive interlocking test has exponential complexity with the number of puzzle pieces n, making the approach not scalable. Our key idea is to solve this challenge problem is to make a connection between interlocking assemblies and a specific graph representation. These graphs are called directional blocking graphs, invented by Wilson in 1992 for assembly planning. Based on this connection, we can test interlocking much more efficiently. We show that if all these directly connected graphs are strongly connected except the key, then the corresponding puzzle assembly is global interlocking. Thus, we can test interlocking in the graph domain rather than in the geometry domain with polynomial time complexity. Next, I'm going to illustrate our graph-based approach to test interlocking on this simple 2D example. If a puzzle assembly is interlocking, all paths and path group should not be able to translate along any actual direction except the key. Let us first consider the path translational motion on the positive x direction. The red part is blocked by the blue part from moving along positive x. See the contact highlighted in black on the left. Hence, we draw a direct edge from the red to the blue part to represent this blocking relation. Similarly, we draw a direct edge from the red to the orange part to represent the blocking relation between them. For every blocking relation along the positive x in the geometry, we draw a corresponding direct edge in the graph. By this, we create a directional blocking graph for positive x direction, denoted as G positive x. We can do the same procedure for the positive y direction and create a directional blocking graph for positive y. These two graphs are called the base directional blocking graphs of the assembly. We have shown that the assembly is interlocking if all its base directional blocking graphs are strongly connected except the key. The complexity of this testing approach is polynomial, since finding all strongly connected components in a graph can be done in big O n to the power 2. These directed graphs can also be used for designing interlocking assemblies. The key idea is to break interlocking design into 2 stages. The first stage is to make the graph strongly connected, and the second stage is to use these graphs to guide the search of corresponding path assembly. Next, I will show you how to use these graphs to design interlocking assemblies on a simple 2D example. Our input is a regular grid denoted as R0, and our goal is to partition it into 5-part interlocking assembly. Our idea is to do the partitioning iteratively and ensure interlocking for each intermediate assembly. We first do the splitting in the graph domain to partition R0 into P1 and R1. By adding new direct edges between P1 and R1, we can make the graph strongly connected except the key. Next, we realize the graph design in the embedded geometry by creating blocking relation corresponding to each new direct edges. By this, we obtain an intermediate assembly that is interlocking geometrically. Next, we further partition R1 into P2 and R2 in the graphs, and make the graph strongly connected except the key by adding new edges. We further realize this graph design in the embedded geometry to form a 3-part interlocking assembly. We do this graph design and geometry realization iteratively until reaching the desired number of parts, such as the 5-piece interlocking puzzle shown here. In this work, we use a tree-based traverse approach with backtracking to explore the search space of interlocking configurations. I will skip the details here. Here we compare the DBG-based approach with approach in 2012. Given the same input, the new approach can find a larger number of puzzle pieces. And our approach supports 18 additional constraints when designing interlocking puzzles. See this 40-piece interlocking dog is eyes, ears, and tail from each individual puzzle piece. And here is the assembly animation, and you can see the geometry of the puzzle pieces clearly. Here is another example. It's a interlocking puzzle cube with 1,300 parts. This model shows the scalability of our approach to design interlocking puzzles with a huge number of puzzle pieces. Okay, so now let me introduce the second research work about designing high-level interlocking puzzles. In this research work, we propose a computational approach that enables general users to design an interlocking puzzle with user-specified level of difficulty and appearance. Here is a preview of our generated puzzle. We also fabricate the puzzle using 3D color printing. Our design problem also can be formulated as a shape decomposition problem. Taking a box-sized shape as an input, we computationally design a level L interlocking puzzle by partitioning the shape into K puzzle pieces, where the box-sized shape L and K are specified by users. Note that we also use the iterative shape decomposition framework to ensure the 4 basic design requirements. There are 3 challenges to design high-level interlocking puzzles. The first challenge is how to compute the level of difficulty, which is the minimum number of moves to take out the first sub-assembly. This requires enumerating all possible disassembly planes to take out the first sub-assembly. Look at this example. Given the same puzzle, we have 2 different planes to take out the first puzzle piece in green color. And the top plane has a smaller number of moves by moving the yellow and blue pieces together. The second challenge is to ensure that the puzzle pieces are interlocking in all the configurations before the sub-assembly is taken out. Look at the 4 puzzle configurations on the left. In each of them, there is no removable puzzle piece or sub-assembly. The third challenge is how to extend our computational design approach to generate puzzles with smooth appearance, so that a single CSG intersection operation between the input smooth shape and the box-sized puzzle pieces may result in structurally weak puzzle pieces, as highlighted by the red circles. To address the challenge, we propose an approach with 3 contributions. So first, we propose a graph-based disassembly planner to compute the level of difficulty. Second, we present a computational framework for constructing the geometry of each puzzle piece. And third, we formulate and solve a shape optimization problem to generate high-level interlocking puzzles with smooth appearance and structurally sound pieces. First, we propose a kernel disassembly graph to compute the level of difficulty of a given interlocking puzzle. In this kernel disassembly graph, each node is a puzzle configuration, and each edge represents the transfer from a puzzle configuration to another puzzle configuration by a single move. Root node represents the initial puzzle configuration. See the node at the top of the graph. A target node is a puzzle configuration where only one puzzle piece of sub-assembly is removed. In this example, we have 3 target nodes highlighted with rectangles. A kernel disassembly plane is a path from the root node to a target node. There may exist many kernel disassembly planes. We show 2 kernel disassembly planes in yellow and red color respectively. The yellow path takes 5 moves to take out the green piece, while the red path takes 8 moves to take out the pink piece. To compute level of difficulty, we first compute the asserted path from the root node to each target node, and then choose the path with the minimum number of edges. Our second contribution is computational design framework, where the key idea is to construct each puzzle piece iteratively to expand the disassembly graph. Starting from the input shape, we construct the first puzzle piece in green and ensure that the new puzzle piece is movable but not removable to create a new node in the disassembly graph. Next, we construct each puzzle piece in a puzzle configuration that is furthest away from the root node. We make the new puzzle piece movable to expand the disassembly graph while ensuring that there is no removable subassembly. We iterate this puzzle piece construction process until the sixth last puzzle piece is constructed. When we constructing the last puzzle piece, we aim to make the resulting puzzle disassemblable and interlocking. By this, we ensure that the resulting puzzle is disassemblable and has a large disassembly graph, which is necessary for achieving a high level of difficulty. Our third contribution is shape optimization for visualization. As aforementioned, directly performing CSG intersection between each visualized puzzle piece and input smooth shape result in structurally weak pieces. Our observation is that these structurally weak puzzle pieces are always caused by problematic voxels that cover tiny input smooth shape. Hence, we propose to transform and slightly deform the input smooth shape to minimize the number of problematic voxels, as well as minimize modification on the input smooth shape. Here we show the input smooth shape before and after the shape optimization, which reduce the percentage of problematic voxels from 23% to 11%. The optimized shape is close to the original one and looks like being inflated to fill the visualization as much as possible. And the optimized smooth shape leads to structured sound pieces, as shown on the right. Results. So here is a level 10 angry bird with smooth appearance generated by our approach. Here is a level 27 interlocking cube, meaning that it requires 27 moves to take out the first puzzle piece. Here are the puzzles we fabricated using 3D color printing. We conduct a user study to know how difficult for general users to play our high-level interlocking puzzles. So I will skip this part due to the time limit. Okay, summary. So in this talk, I will first, the puzzle solving is a disassembly planning problem, and some puzzles may require complex disassembly plans to solve them. And puzzle design is a geometry modeling problem with a number of design requirements on the fabrication, assembly, appearance, and applicability. So I have given an overview about the state of the art and introduced two research works. Future work. Assembly planning is a fundamental problem. So computing complex disassembly plans remains a challenging task that has not been fully addressed. Disassembly planning with flexible parts is quite common in mechanical engineering since some mechanical parts are flexible. However, the problem is even more challenging. And the computational design of specific geometry puzzles and study interesting geometry problems in puzzles is also can be also a future work. And also last future work is to explore potential applications of geometry puzzles. Okay, so that's all for this talk. Thank you for your attention.
Thank you, Peng, for this very nice and very interesting talk. And now we open for the questions from the audience. So to give more time to our assistant to collect questions, I will read some questions firstly. Actually, this is a very interesting talk, and it has so many variations, as you have mentioned. Yeah, and I have one question related to the scalability. Yeah, I wonder whether you have considered this scalability of this puzzle in this puzzle design. For example, if the size Now the size is kind of like the normal size, like our daily objects. But what it will be, whether it will involve new challenges if we consider much larger objects, like in architecture. It's because since one part when this part is getting very large, and I guess it will involve more like physical issues.
Exactly. Yeah. Okay, thank you, Professor Luni, for the question. I think that's a very good question. Okay, so I mean, because in this talk we focus on puzzles, so we can only focus on the geometry, so we can ignore lots of problems relevant to physics. Okay, but in case we want to apply this, I mean, the techniques for large scale like architecture, so there are lots of things we need to consider. For example, when we assemble the puzzles, it's very easy. We just use our hand to assemble because it is small. But if we want to assemble architectural parts, it's big, it's huge. So I mean, how can we minimize the scaffold? How can we compute the assembly sequence that can that is easiest for the construction process, right? So I mean that will introduce additional problems, and also structural stability. So for puzzles, I mean, the structural stability no need to be so serious. As long as it can stand by itself, it's fine, right? Because it's just for playing. But for architecture, I mean, the structural stability should be more serious. That means it's not just to bear its own weight, but also need to bear up some other external forces. Yeah, so I think that these can be interesting future work. Yeah, to I mean, not just consider the geometry, but also some properties in physics.
Yes, thank you for the comment. Actually, you have already mentioned some like flexible materials, flexible mechanisms in your future work, future slides. Yeah.
That is another trend. That is actually the application in mechanical engineering. Because in mechanical engineering, there are usually rigid parts and soft parts. So how to solve this assembly planning problem is actually, I mean, still a research problem. There are very few research work on this topic. Because it's very hard. Because when you do the assembly planning, you not only need to consider the geometry constraints, but also the deformation of the parts. So it's very challenging. So very few research work on this topic.
Yeah, as we see, I think it has similar issues in molding. We have soft materials for molding, and also we have this rigid material. It's
very good point. And we also do some, I mean, experiment on the molding. Actually, the mold itself can be an assembly, and so it's also considered as assembly. So I mean, similar issues. Yeah.
Right. Exactly. Yes. It's just this like the dual question on which part we to contribute. Yeah.
Exactly. They have the same assembly planning problem. Which piece to take out first? Yeah.
Exactly. Yes. So so even though it's already a pure interesting geometric problem, it involves so many potential applications and more issues to be considered.
Yeah. Exactly. Yeah.
Yes. And I think I have one question from the audience, but it's very interesting, and he wonders whether such models can be downloaded, or whether there are some codes they can have a try.
Yeah, we have.
Do we have models online?
We have models. Okay, so we have the models on our group page, and for this high level interlocking puzzle project, actually we have released the code. So if some students or researchers are interested, they can try the code.
Wow, very good.
And we also have the models on our page, so they can download and do the 3D printing.
Yeah, that would be really such like meets this core interest of these physical objects.
Yeah.
Okay. Due to the time limit, so I think we conclude the first talk, and thank you, Peng-Song, again for this very nice talk.
Okay, thank you.
And now I will check this take the honor to introduce our second speaker. Okay, so now I take the honor to introduce our second speaker. Second speaker is Haisen Zhao from Shandong University, and his talk will be in efficient design and fabrication for complex geometries. Haisen Zhao is a professor at the School of Computer Science and Technology in Shandong University. Actually, he's also my colleague. And his research interest lies in computer graphics and their application for digital fabrication. He completed his PhD at Shandong University under supervision of Professor Baoqian Chen, and received master's and bachelor degrees also from Shandong University. And Haisen Zhao was postdoctoral at the University of Washington, working with Professor Adriana from 2019 and 2021. And he was postdoctoral at the Institute of Science and Technology at Austria, as well as ST Austria, working with Professor Bernd Bickel recently for 1 year. And he received the first prize of Shandong Natural Science Award at Shandong Province, in 2020, and the doctoral dissertation award from CCF in 2019. And so let's welcome Haisen Zhao for the talk. And now the floor is yours.
Okay, can you hear me? Okay.
Yes.
I will share my screen. Okay, can you see my slides?
Yes.
Okay.
Yeah, very good.
Cool. Okay, it's my time. Okay. Good evening, everyone. Thanks introduction. Thanks Linda for introduction. It's really my pleasure to give a talk at AsiaGraphics. This is my outline of this of today's talk. For the first part, I would like to briefly introduce myself. Even though Linda Lu have introduced myself, I will give some images to show you. My research work mainly focused on computer graphics and the geometry process and their application in digital fabrication. I have just got a professor faculty position at the Shandong University. Indeed, the Shandong University is also where I got my PhD degree, advised by Baoqian Chen. Here I saw some pictures of our campus, our really nice campus, which is located near the sea. So you can see with many very beautiful views. I introduced by Linda. I have two stages of postdoc experiments. One is 2 years postdoc fellowship at the University of Washington, and another one is in Austria, in STA, advised by Bernd Bickel. Here, I just want to show you some pictures, really nice pictures of the two campuses and my research groups at the two universities. Okay, before talking about my own research, I would like to introduce the background of my work. Take a look at this image. The fabrication process still in our industry still involve significant human effort during the design and the manufacturing process. Given this background, my research, the goal of my research is to improve the production process and reduce the amount of human effort required in the design and the fabrication. So in a bit summary, my main goal is I want to produce many computational tools for the next industry revolution. So why? So what's the key benefit of this direction? Firstly, it is used to answer this problem: what we can make. We need to design products of specific functions, such as interactive structures, multi-material products, or functional textiles. And the second problem we can answer is how we can make it. We need to generate the fabrication plans in a low cost, efficient, or robust manner. Here is another answer to the same problem of why we want to build such tools to help make sense. This answer is a mathematical formulation from Professor Jim Mokan of the CMU. I just read his test, given that there are instances to be created or design or fabrication. Each always take effort E, then result of cost R can reduce the E to E prime. Note that in the industry or in our common life, here in the equation, the E can be a really large number. It can be a million or a billion, so it's a really large number. Therefore, even if the E prime is only a bit better than the E, it can still very useful. It means we can save a lot of money or other benefit from this. So I really like this equation to solve why we want to build tools to help make sense. So what problem I have worked on in my research? Okay. All my existing work can be grouped into three subjects. For first one, for first topic, we would like to speed up the product upgradation process by reducing the iteration between the designer and the fabrication engineering. What's the meaning of this problem? I want to talk about more. For fabrication, we always start from a design, and then we would like to optimize the fabrication process for what model to minimize fabrication cost. During this process, this is important because the fabrication is design dependent. However, when we design, creating or modeling a design for its physical behavior, we need to consider or understand the fabrication process as the fabrication process indeed is define the physical what we can physically realize. So from the picture we can see a cupping relationship between the design and the fabrication. So with the cupping relationship make the optimization really challenging. We want to explore this challenge problem on the computational domain. For example, imagine if we want to fabricate this simple birdhouse, this can be done with many different cutting tools, bandsaw, jigsaw, table saw, or chop saw. Also, packing and cutting in the different ways or different orders can have many different options. All of these decisions or options of cutting tools, or packing or cutting orders will affect the fabrication time, material cost, or even the overall precisions. So this problem is really hard. For this problem, we want to solve it. Our key insight is that we find that both design and the fabrication can be programs. For design, the design process can be expressed as a sequence of geometric operations. It can be a code. And for fabrication plans, it's also a sequence of physical instructions. With this insight, we argue that this insight can help us solve this problem in design for fabrication by draw ideas from program language domain. In the programming language domain, there is a very famous data structure called the E-graph. The key benefit of E-graph is it can compactly and efficiently represent large-scale equivalent program. What's the meaning of that? Even though you may did not hear about of the E-graph, you may use it in some favorite in some math software. when you call the simplify, a function called simplify in your in some math software. The idea is that there are two programs are equivalent, and we can go from one program to another one with a sequence of result rules, all called equivalent rules. The space of equivalent is very hard to search, and the eGraph can define a data structure that makes this search tractable. Originally, the eGraph cannot use the for carpentry domain directly. We overcome this gap, this problem, by produce the reusability problem and propose a geometric method to populate the eGraph. Here, as others ignore some technical details, the key idea is we generate many geometric result rules, geometric equivalent rules to populate the carpentry eGraph. Based on the carpentry eGraph, we can optimize. We can do a multi-objective optimization. Here I just show some results. We have asked 3 carpenters to design carpentry models use our framework, and here are the results of the design. And the one key benefit of our approach is that our framework can return not only one but multiple solutions with different trade-offs, and allow user to explore what they want, to select what they want. So we also compare with some compare our method with some skilled carpenters. For most cases, our system can find better solutions than the expert. Okay, for now, we can get some optimal fabrication plan for given design, but we did not consider to optimize the design itself. What if we want to optimize the design itself? Why do we want to optimize the design itself? What's the key? What's the benefit? Here is one example. Here, for this example, consider this model. The following figures show the lowest time cost and the lowest material cost fabrication plans. We can generate design variations by discrete varying the joints of the input design with the 2 design variations. Now we are able to generate a fabrication plan that is 30% faster to the material for fabrication, and one that can reduce the material cost by 15%. So in this work, we propose a new method that allows users to consider the space of possible design variations when optimized for fabrication plans. Indeed, this problem is a typical multi-level optimization problem, where each carpentry design variation determine a large-scale certain space for fabrication plan. And our key insight to solve this is that equivalent substructures within a single design and across different design variations. Also, based on the eGraph data structures, we propose a new eGraph called a bag of parts eGraph to represent the design and the fabrication in a single certain space. Even we use eGraph, the certain space is still really large. So how do we search? How do we optimize based on the bag of part eGraph? We propose an iterative create extraction algorithm. Also, I'll skip the detail of this algorithm. For results, we have tested our method on this different kind of geometries. As shown, in this example, we can further reduce the fabrication time and the material cost by including some new design variations. This slide shows the fabrication time. more results, we saw the number with the percentage. For the material cost, we computed the material cost by the money, by the dollar number. We can reduce the material cost by including some new design variations. Here are some more results. Okay. For my second subject, we aim to improve fabrication efficiency and the quality, particularly for some complex geometries. However, the fabrication plan for complex geometries always still require some human effort, such as the fixture design and the setup planning process. In this topic, I will talk about 3 projects. For the first one, we focused on 2-pass planning for 3D printing. In 3D printing domain, the zigzag is the most popular field patterns. However, zigzag field patterns have 2 key drawbacks. One is discontinuity. The second is there are so many subtrains as shown in this animation. So ideal of 2-pass should be a long and a continuous 2-pass with low curvature. To get such ideal 2-pass, our key in the idea is to include the formula spiral. Here is a formula spiral for square region. Compared to original spiral or single spiral, we can find that its start and end point are all along the region boundary, and the two endpoints can be placed anywhere on the region boundary. With the 2 observations, we can allow to connect it multi-furnace spiral to be a single 2-pass, as shown in this figure. So in this work, we introduce a new 2-pass called connected formula spiral, which achieve global continuity and form as a long and low curvature 2-pass, as shown in this butterfly. For results, we have tested our method on a set of shapes with different degree of complexities. The connected formula spiral is very suitable for this kind of shapes with honeycomb input shapes with all 2D slicer layers of 3D porous structures produced by our another paper. Imagine that if we use the zigzag 2-pass to fill such shape, there will be many subtrains and many non-continuous 2-pass. Just like 3D printing, we also need to do the 2-pass planning for subtractive manufacturing. Instead of filling 2D layers, we must carve over curved surfaces. So an interesting question is, can we apply connected formula spiral from 2D to 3D to freeform 3D objects? Another difference is that we would like to consider curved surface quality by generating uniform distributed scallop, which the scallop is a residue material that is left by the cutter after carving, just like as shown in this figure. Our basic idea to achieve the uniform distribution scallop is to compute an adaptive scalar field whose ISO line can meet the gap requirement. Here are some results. In this work, we propose a so-called ISO scallop connected formula spiral 2-pass. These 2-pass have global continuity, continuous, and uniform scallop distribution. There are 3 properties. We also test this 2-pass by fabricating a set of real 3D objects, as shown in these short videos. Okay, the final project along this topic is in-system machining of 3 axes, because it's only 3 axes. So it's often not possible to machining a freeform shape from a single direction. We always need to multi directions to finish the machining. In practice, each direction needs one setup for machining, which is a very expensive process. You can see from the video, it's very expensive process. During this topic, during this project, we propose a new geometry property called curvability to describe such volume. Indeed, it's a new geometry property. Indeed, it's just a combine between the visibility and the monotonicity. And we have a new formulation for this problem. We gave the first formulation of the problem as a volume decomposition problem to minimize the number of setup directions and the number of couple volume. Note that the couple volume, it means we can use a single toolpath to machining this volume. Also, I saw some results. We have compared on the left side, our algorithm produce 3 directions. We compare our method with some expert. We can see we use 3 directions, but the expert have to use 6 directions. We can get better results. This is another comparison. For 3D comparisons, we use a simulation process to compare the current time of the direction provided by expert against ours. In all the cases, our algorithm is much faster. Okay, for a third subject, we aim to design new products with some physical requirement, just as the discussion between Linda and Peng. I will also talk about 3 papers, 3 topics, 3 projects along this topic. For first work, we have introduced a new method for generating perforated lampshade that can project a continuous grayscale image on a surrounding wall. In order to generate a grayscale image distributed on a surrounding wall, we perforate the lampshade with a set of tubes with varying density of each tube, then varying its radius and tilting angles. Indeed, this work can be seen as a 3D half-toning technique, where the basic elements are not 2D dots, but 3D tiny tubes in a thin lampshade cells have both radius or rotation respect to the light source. For each tube, the light passes through from it which can generate a footprint on the wall. Also, I saw some results of this project. Here are a set of fabricated spherical lampshade. The left is projected image, so the real photographs of this lampshade. Okay, my second project on this topic is a reverse engineering project. The problem is that given a set of images, can we generate a fabricable geometry models? Our key insight is to present object use the fabrication process itself when we do the reverse engineering. In this work, we use a 2D contour and a 1D thickness to describe each part. Here we saw some results. This image shows some results generated by our results. From this image, our framework can generate the footprint or the blueprint, which can be directly fabricable by by the user. Okay, as the final project along this topic, we have been inspired by some powder structure for 3D printing to generate the honeycomb cell structures which can resistant and external stress with minimal material cost. Here we saw some more results of such structures. Okay, my next session I would like briefly just introduce several fields work along my existing works. Okay, here is I have got 3 very specific directions. The first follow-up of existing work is to continue working on the co-optimization between design and optimization. I would like to introduce continuous parameter for generating design variation, such as length, width, and angle. My previous existing work only consider discrete parameters. It's easy to imagine if we including the continuous parameter, it will extremely enlarge the certain space. How do we solve it? It became very challenging. The second specific topic is to include some physical properties during the fabrication plans. For my project, I have been working on the 2-pass planning, but during the 2-pass planning, we did not consider the physical problem during the optimization. For this, I want to can we take the physical constraint during the 2-pass planning? It's a challenge problem. For the third topic, specific idea is called hybrid manufacturing. You can see I have been working on 3D printing or subtractive manufacturing or molding or many other fabrication process. I also imagine can we combine this different kind of material technique, different fabrication techniques. For this specific idea, there are many commercial 3D printing and CNC machining hybrid manufacturing machine. I know there are many such kind of machine, but this kind of machine can only produce very simple geometries. The key challenge is they need some computational tools to generate the fabrication plan for the complex geometries. So we really want to do these directions. I also wanted to do some other hybrid manufacturing between different techniques. Here, so a complex roadmap of this project. In my following projects, I really want to use some data-driven method or some human-in-the-loop method to solve this kind of geometry, design, or fabrication problems. Okay, my final part is a very short summary. My existing research work, my whole research is try to apply graphics technique to produce computational tools for design and fabrications to solve what we can make or how we can make the two problems. Okay, that's my summary. And thanks for your time and attend my talk. I'm looking forward in the following Q&A sections.
Okay, thank you, Hassan, for this very nice and very informative talk. And again, so we are now open for questions and comments from the audience. So do not hesitate to post your comments or questions in the chat box, no matter what channels you're watching. And so I will start from one or two small questions. So the first one is related to the to the carpentry work. You have a series of carpentry works that integrates the design and the fabrication.
Yeah.
So according to we have the first talk from Professor Peng Song related to these geometric puzzles. I think there are a lot of common points between these two issues. There's the puzzles and the carpentries. As your carpentry is also, at least it looks like the puzzles. It comes from smart decomposition rules, and you need to also consider the assembly sequence, right? So do you have any like comments whether such puzzle, such like this, like interlocking or some other issues can be further applied to this carpentry?
Yeah, I was thinking. Firstly, I want to say for a carpentry domain, it to belong to a subtractive manufacturing, because the input is a big carpentry board. We cut some pieces, some shapes from the big pieces. So it's subtractive manufacturing. But for the for Peng Song's work, the ensemble, we can say it's more like if we assemble during the assemble process, it's additive manufacturing. It's additive manufacturing. But one so this point is different. One is subtractive, one is additive. But when we work on the carpentry domain, we would like to extend the co-optimization between design and fabrication to other domains, including the additive manufacturing. But this indeed is really challenging. As discussion from you and Peng, in his work, he did not consider counter work. He did not consider multi physical property during the design. Indeed, here it's the co-optimization between design and the fabrication process. For a carpentry, it's became simple because firstly it's 2D. It's 2D. Another is there no the order is not there are no indeed for a carpentry problem. There are no assemble. We did not consider assemble. We just consider the fabrication process. Each part is independent, but we have for the assemble process. Yeah, for sure we need to assemble each part to form a chair, but we did not consider the assemble process in our process. For assemble process, it's order dependent, and for Peng Song's is also order dependent. If we want to consider the design optimization and the fabrication process, also the assembly process, if we want to do the optimization, combine the 3 states. The problem is too challenging. Another difference is for carpentry, for our current method is only can only used for discrete parameter. We did not consider continuous parameter. But for example, for 3D printing, there are many continuous parameters, just as Peng Song's work. But for some example, for some assemble is also discrete. It's also discrete. Not so many continuous parameters. Maybe we can use the eGraph technique for some discrete additive manufacturing. Make it simple. We can start from
very detailed.
Yeah. Okay.
Yeah, And Peng Song also have a question, and I encourage him to ask you directly. So please.
Okay.
Hey, hi, Hassan. Thanks
Yeah,
for
long time no see.
thanks for a nice talk. I have one question about this commentary project. Okay, so for this furniture, right? So on the market, lots of them actually they have this joints, integral joints, right? So so if you buy some furniture from IKEA, so actually they already have the joints, right? So, when you bring the parts, you can assemble by yourself. So I just wondering whether this integral joints is possible to be incorporated in your carpentry project. When you fabricate the parts, it already have joints like some holes or extrusions.
Yeah. Indeed, we have considered we want to do this because for carpentry the joints is very complex. Even for this, we can generate some many complex joints to combine the two parts. But for now, we did not consider that. In our current work, we only consider very simple joints, very simple joints. And another point I want to say is different joints will affect the stress, the physical performance, such as how many stress it can resist. Our current work is also did not consider this, but I believe our work is general enough, can take that such consideration into. It's just to add another objective. Our current objective is we have three objectives. It's all fabrication related, fabrication time, material cost, and precision. In our paper, we have shown one example to evaluate the physical performance, how many stress it can resist. We have one single demo to show that. I think because it's related to the joints, different joints will have different stress performance.
Exactly.
Yeah.
I think that can be an interesting future work. How to fabricate the furniture parts with joints more efficiently.
Yeah. It's also how to fabricate exactly. Such very complex joints. It's very interesting.
Yeah.
Our current part is pretty simple.
Okay.
It's kind of our current carpentry is do the rough machining, or is do a rough part. We did not consider to make each part have more detail, more geometry detail. Yeah.
Okay.
We can go further. Yeah.
Okay. Thank you.
Yeah. Thank you.
Yeah, and even if you consider joints in the blueprint, also this processing time, assembly complexity and assembly time will also be highly affected.
Yeah.
But it's really like your workflow, like this kind of rough machining and fine machining. It's like these two stages.
Yeah, rough machining and fine machining. Yeah,
very interesting. And if you further consider hybrid manufacturing, I wonder whether this carpentry can be further extended to more general materials, or more general like the applications. Because for carpentry, you only need to consider this so-called subtractive manufacturing. You only need to do this cutting and assembly. But maybe for more general materials, you can consider more. You can evolve this hybrid manufacturing methods in the design, like metal, like plastics, like some other or some soft materials in the loop. It also implies many interesting directions.
Yeah. We can. Oh, it's really a good idea to combine this my first topic and the third topic. We have considered to involve 3D printing to the carpentry. It's kind of for a chair, for wood chair. We can printing on the wood. It will ask us to do the optimization. When do we do the cut? When do we do the 3D printing? Maybe we can generate some new art, some new product combine the wood and the plastic material. Yeah, it's crazy.
Yeah. And I really think your two very good talks have some relevance, have some really high relevance inside. Yeah. Okay, so Peng-Song, do you have further comments or questions?
Okay.
If no, okay.
Yeah, I have one last question. Okay, so I just want to ask Hyson. So you mentioned about hybrid fabrication, right? So you combine additive manufacturing and subtract manufacturing. I'm just wondering, is this commercially available or is it still under research?
Yeah, it's available. Then you can see many such kind of machine, but it's mainly for metal, for metal material. It's not common for plastic. It's not always fabrication with plastic, just as common FDM machine.
Okay,
it's always use some metal powder.
Okay, so for the additive manufacturing and the subtractive manufacturing, do they use the same material, the same metal material, or different materials?
Commonly they use metal. They use same. They first use 3D printing, 3D additive manufacturing to generate a 3D shape.
Yeah.
Then do the machining, do the fine machining over the surface, over the rough surface. Because there are many such kind of machines.
Yeah, I knew. I mean, for this currently, so for this metal 3D printing, right? So I mean, they can do this 3D printing, but the surface quality is not good. So that's why they use CNC machining to do the polishing.
Yeah. I also noticed that in our domain, there are many work focused on the plastic FDM method, but for the metal, I did not see any paper in graphics domain work on it. Metal related fabrication.
I know. I mean, they have this technique. Okay, I just wondering, when they do the fabrication, do the machine do it together? I mean, for example, one part is by additive, another part by subtractive, or is do it independently? Because I know that
it's additive. It's additive. First, use 3D printing method to generate a part, but the part have some layer staircase. For staircase, we can use the machining, use a cutter.
Okay.
To carve over the surface.
Okay.
To make it very smooth.
Okay, I see. Okay, so I mean, yeah, that's reasonable. I mean, let's combine the complementary strengths of the two techniques.
I have also considered other hybrid, such as 3D printing and molding.
Okay.
3D printing and molding, we can also consider to hybrid.
Yeah, exactly. Okay, that's can also be an interesting research topic.
Yeah. Thank you.
Okay, thank you, Hassan.
Yeah.
Okay, Professor Neil, so do I have further questions?
No, I don't have further questions. And I have extra comments. And as you mentioned, this additive and subtractive are independent. They do not interfere, but they perform interleavingly on the same part. Yeah, so they are independent to each other.
Yeah.
Very, very cool. Okay, so Hassan, do you have any questions to the first talk? If no,
you have asked what I want to ask. I also want to ask Peng, have you how challenge if you want to fabricate your design?
Okay, so I mean, if you use 3D printing, then there is no challenge. I mean,
No challenge.
okay, because okay, so the properties, I mean, the although it looks complex, right? But for 3D printing, especially we can use this 3D printing with water soluble material. So I mean, no, we don't need to care about the spot because it's water soluble. We just put in water and the spot will go away. So there's no challenge to do the fabrication in terms of 3D printing. And because it's small, so 3D printing is okay. It's only take maybe 10 or 12 hours to fabricate a puzzle. So it's not a big issue.
Yeah, I have another comment. It's not a research. It's not a research problem. It's just you have to. I know you have to do this topic for many years. Have you considered to do some commercial applications to have a company to have to have common users can.
Okay. Okay. At this moment, I will focus on research. Maybe later, maybe a few years later, maybe I can consider this. But at this moment, I mean, the focus is it's for research.
Okay.
And actually, I actually for some of this project, I released the code. So that means
really cool.
anyone can use the tool to design their puzzles.
Yeah, it's really cool.
Yeah.
Okay. Thank you. It's really good for the community and such that more people can be involved in this very interesting topic. It really, I think we still have many further projects to follow up. This related to this puzzle direction.
Exactly. Actually, I encourage students and researchers to study these problems. Actually, it's quite interesting. Yeah.
Yes, exactly. And also, you have this very neat formulation, geometry formulation, and also you have the very real objects and really
okay. So so the puzzles, although so this looks quite a very small market, right? But the good thing of design puzzles is that you don't need to care about the physics. You only can only focus on the geometry.
Oh, exactly. Yes.
Yeah, that's the good thing of doing research.
Yeah.
Exactly. Yes. Yeah. Very good. Okay. So since we have discussed a lot, and I would like to conclude this session, and thank you again for this very nice talks. And thank you for all the audience if you are still watching our live stream. And okay, so that's all for today's session. Thank you.
Okay, thank you, Nuni, and thank you, Hassan. Okay, bye-bye.
Yeah, see you.
See you.
Bye. 那可以就撤了，是吧？Hello。